Let me see it again. Okay, the next speaker is Dr. Solomon Bakala. He's working at the Berhan University, Department of Mathematics in Ethiopia. The title of his talk is Approximation of Common Solution of Nonlinear Problem in Banach Space. Dr. Solomon, you can continue.
Okay, thank you, Dr. Mata, and thank you for organizer for this talk. My presentation is approximation of common solution of nonlinear problems in Banach space. I think it is not move. Yeah, we have the outlines of this presentation. We have introduction, background of the study, and definition, and we have some review literatures, and we have two main results for this talk. We have some notation that means n is a set of natural number, r is a set of real numbers, and e is real numbers, and e star is dual space of, and we can apply for this background of the study. That means fixed point theory is a beautiful mixture of analysis, topology, and geometry. With it is defined as fixed point means that means t, we have t is an operators from C to A, t of p is equals to p, and we have play very important roles in many different fields: optimization theory, differential equation, equilibrium problems, image recovery, game theory, and cultural theory, and so on. For some review for this application, that means for optimization problems, we have considered the minimization problem f of x plus g. We have minimized two functions. F is a convex and smooth function, and g is from a to r is convex and lower semi-continuous function. That means f is differentiable. That means the gradient. We can solve the by Fermat's rules. We can find the zeros of a plus b, means the minimization of this one, that this problem 3 is changes to a minimization problems. The other one is the generalized mixed equilibrium problems. The generalized mixed equilibrium problem means we have bidual functions. That means f and phi is a real valued function, b is a monotone nonlinear mapping in general. That general mixed equilibrium problem is we are finding f, the solutions of this one is a generalized mixed equilibrium problems, and we have some conditions to get the solution of this generalized mixed equilibrium problems. That means condition A, that f of x is equal, we have a1, a2, a3, and a4 are fulfilled. We have the solution of this generalized mixed equilibrium R exists. If we have some special case for the generalized mixed equilibrium problems, we have general equilibrium problem. That means psi is equals to 0 for problem 4, and denoted by g of p. And if f is equals to 0, then that means the generalized mixed equilibrium problem are changes to that mixed variational inequality Broders type. And if p and phi r is equals to 0, that means we have changes to an equilibrium problems. We have changed also f and phi r variational inequality problems. That means variational inequality problem is a subset of mixed variational inequality problem. That is a subset of equilibrium problem and generalized equilibrium problem. This more general one is a generalized mixed equilibrium problems. So from this generalized mixed equilibrium problems is changes to as a fixed point problems. That means the generalized mixed equilibrium problem are equivalent to, that means t of f is a single valued mapping for equation 5. That means the fixed point of this operator is equivalent to the solution sets of the generalized mixed equilibrium problems. And the generalized mixed equilibrium problem are just closed and convex. So we have, for this one, we have to satisfy condition A. For specifically, we have applying for optimization problem for the generalized mixed equilibrium problem is also equivalent. We have changed any optimization problems. That means we have take, for example, this optimization problem, g of x plus the norm of x minus u squared minus h. This function, this g is e, h, and g are convex and lower semi-continuous differentiable function. Therefore, this equilibrium problem are changes to a generalized equilibrium problem that is equivalent. That means by taking this f of x is the gradient of g of x, that means this g is a differentiable function, therefore we have a gradient. Therefore, we have forming this f is in a form of this one, and b is in a gradient of this h is also a lower semi-continuous function and differentiable. We can represent in a form of this one. Therefore, this optimizes this minimization problem are changes to a generalized mixed equilibrium problem. So we have changing in a form of, we have satisfying these two conditions. The optimization problem are changes to a generalized mixed equilibrium problems. The next one is we have differential equation, nonlinear evolutional equation. That means the derivative of x plus b of x is equals to 0. This problem are changes to form of, if v is equals to 0, that means an equilibrium state. To find the equilibrium state of the function, we have, that means this b of x is equals to 0. In broader 1967, we have introduced this t is equals to I minus b in a real Banach space. It is called pseudo-contractive mapping. That means we have considering this b is an accurate map. So the fixed points of this operator t is the solution of b of x, and that means the equilibrium states of this nonlinear evolutional equation. So if we have, that one is an accurate mapping, but if the mapping is monotone mapping, that means the mapping T is maps from C to E star. So for the dual space of E, in that case, the solutions that differential operator are the solution of the solution of that differential operator are not getting in E. So we can change that fixed point are adopted in a form of f fixed point problem. That means 2 of p is equals to the gradient of f of p, and the existence of the fixed point, the gradient of f of x is equals to t of x is equals to the gradient of f minus b of x. That means the solution of b of x in the case of if b is monotone mapping, we have mapped from E to E stars. Therefore, this T is F pseudo-contractive mapping. This is defined by Zagaye and Gaetahon. Therefore, if we have adopted for simple common solution of the generalized mixed equilibrium problem and F fixed point, that means if we have considering this type of minimization, that means constraint minimization problems, that g of x plus the norm of h of x minus h in the previous one, subject to SY is equals to 0. That means if we have an evolutionary, the constraints are evolutionary nonlinear problems, that means differential equations. In the case of that one, to solve such type of problems, we have changed as a form of a common solution of a generalized equilibrium problem and f fixed point. So we have finding the common solution of the generalized mixed equilibrium problem and f fixed points of. That means this example are changes to a common solution of a generalized mixed equilibrium problems and f fixed point. Now we have the basic definition. That means to get the gradient of f, we have F is Gauss differentiable and a strongly convex function. We have defined by this one. And the next one is Brigman distance. That means we have defined on equation 13, and Brigman projection we have defined in equation 14. So in that case, if we have considering is that irreducible for that means that one is in reflexive Banach space. So if we have E is a smooth and strictly convex space, and we have considering this F is 1 over P norm of P, the gradient of F is equals to the duality mapping J. And if you have P is equals to 2, and this Brigman distance are changes to Lovnan functions, and if P is equals to 2, that means the Brigman projection is changes to generalized mixed projection type. So if we have E is a Hilbert space, and if we have considering F is 1 over norm of x squared, this Brigman distance are changes to y is equals to minus x, and the gradient of F is particularly we have an identity mapping. So we have defined the definition of the operator F pseudo-contractives and gamma strictly F pseudo-contractive, Brigman relatively F pseudo-contractives, semi-pseudo-contractives, that means J non-expansive mappings we have defined on this definition. So every J non-expansive mapping is semi-pseudo-contractive mapping, and E is a smooth and strictly convex, and f of x is equals to 1 over norm of x squared for all of x. In E, F pseudo-contractive mapping is reduced to the semi-pseudo-contractive mapping. Sometimes we have these semi-pseudo-contractive mapping are J pseudo-contractive mappings. F fixed point are reduced to so semi-fixed point T, and E is a Hilbert space, and F is this one. Therefore, F pseudo-contractive mapping is reduced to a pseudo-contractive mapping. That means we have initially borders are defined in 1967. We have pseudo-contractive mappings. That means we have applying on accurate mappings. For F fixed point in Hilbert space, E, that means E is strictly convex and smooth, and F is norm of this one. We have F pseudo fixed point, and we have F fixed point. Therefore, we have a generalized F fixed point is a generalization of a fixed point. F semi-pseudo is F S fixed point, and J fixed point is more general. So if we have the mapping is monotone, means we have defining on 22, and gamma inversely strongly monotone, we can apply this one. So if we have A is a monotone mapping, T is equals to I minus J is a semi-pseudo-contractive mapping. So we have the changing the zeros of the monotone mapping are changes to the FJ fixed point or semi-fixed points of the semi-pseudo-contractive mapping. And if we have T is F pseudo-contractive mapping, A is equals to the gradient of F minus T is monotone. And T is strictly F pseudo-contractive mapping if and only if A is gamma inversely strongly monotone mapping. So we have some review literature for this one. For common solution of variational inequality equilibrium problem, a fixed point of continuous pseudo-contractive mappings. We have Zagaye introduced, we have some algorithm to solve the common solution of pseudo-contractive mappings. That means in 2011, we have developed such algorithm to solve the fixed points of the operators in Hilbert space.
Dr.
And
Salaman, could you go directly to your main results because we are out of time?
Okay.
Yeah. Give him 5 minutes because he started late. Maja.
Okay, we can jump to the main result.
Yeah, no, he can take 5 minutes, I think. Right? Give him 5 minutes. Maja, you are muted. Tell him 5 minutes extra time.
Thank you so much.
Daniel, we can move to the main result. Okay, we have assuming we have some assumptions. Our assumption is we have C is an empty closed convex subsets of uniformly convex and uniformly smooth Banach space, and B is finite family of a continuous monotone mapping. F is a finite family of by function satisfies the condition A, and A is Lipschitz monotone mapping, and TJ is finite family of semi-pseudo contractive mapping. We have assuming this one, and the main algorithm is we have developed these algorithms to get the common solution of the first one is we have solving the variational inequalities, these two, and this one is semi-pseudo contractive as a common solution of fixed points of T mappings, and we have applying for this one we have common solution of for the second one is this is a generalized equilibrium problems. So this algorithm is to find the common solution of variational inequality problem, fixed semi-fixed point, and generalized equilibrium problem. So we have find this let x in this sequence defined by 26, and we have based on our assumption we need to find the sequence are well defined first by lemma 4, and next we can check that this sequence is converges to a common solution of this one. Next we have developing and proved these theorems, and next we can check the numerically based on our assumptions. We have considering L to norm and defined by the C is we have taken some balls, closed ball, unit closed ball, and we have applying T and A, T, B are defined based on this one, and the bilateral functions are defined by this one. The common solution of this algorithm is equals to 0. Next, we can check that algorithm are converges to this one. So we have that the main algorithm are changes to based on our numerical examples. So we have that one is particularly for this algorithm is particularly for our examples. So we can, by taking these parameters, well, we will check. We have initial condition are taken from t is the power of, that means a polynomial function t is the power of 10, t is the power of 5, t is the power of 20, to the power of 20. At iterated 8, we can get the error value are this one. We have graphically, we have more accurate value are, we have if the power are very large for the initial condition for the polynomials, we can get the best solutions. The second result is we have assuming C is an empty closed convex subset. So in that one is uniformly convex and uniformly smooth Banach space. This one is in general for reflexive Banach space. And we have taken TIR F pseudo contractive. For the first one is S pseudo contractive mapping. And we have T is continuous monotone mapping and bilateral functions. For the value, all the others are the same except for the space. we have developed that one is for hybrid iterative algorithm type. This one is helper type algorithms. We have developed the algorithms. This one is for variational. These two are for variational. This is a composite type functions, both of the fixed points of F pseudo-contractive mappings, and this one is the generalized equilibrium problems. So we can develop these algorithms, and we can check from this. The second one is we have checking the boundedness of this algorithm for the well-definedness of to get for a reflexive Banach space. First, we need to find the boundedness of the functions, the sequence, and we can find the convergent subsequence. That means we have applying for every reflexive space. We have every bounded sequence for a reflexive space. We have subsequence.
You have 1 minute.
Converges to the values. Already we have finished. We have common solutions for this algorithm and checking the boundedness of this algorithm. The second one is we have checking the convergence of that sequence to the solution of the common solution of this problem, and checking numerically by taking L2. We have applying AIs are this one. We have numerically already adopted. And we have developed this one is for particular that algorithm is changes to particularly for these numerical examples. We have observing the numerical solution for each initial conditions for this one. Thank you.
All right. Thank you so much, Dr. Solomon. Even if it's a difficult time, you did it. So due to the time constraint, because the next speaker will wait us, if you have question for Dr. Solomon, you can ask him at the end or at the time when the next speaker.
If we miss any